together, so the bond angle in the shape is 107.3 degrees. The name of the molecular shape is trigonal pyramidal. Water has 4 electron-dense regions. The Lewis structure for water shows that it has 2 covalent bonds and 2 pairs of lone electrons. Instead of having a tetrahedral shape with a bond angle of 109.5 degrees, the lone electrons push the shared electron pairs closer together. The VSEPR model shows that the bond angle between the 2 hydrogen atoms is 104.5 degrees. The shape of the molecule is simply called bent. To determine the shape of a molecule, draw a Lewis structure of the molecule and identify the number of sets of shared electrons and lone electron pairs. Note that when figuring VSEPR geometries, double or triple bonds only count as a single pair of shared electrons. You can use this information to figure out the molecular geometry. The name of a shape can help you determine how many pairs of electrons produce that shape. First, look at the number of shared electrons. These indicate the number of terminal atoms in the molecule. The prefix tri means 3, so the presence of 3 terminal atoms produces the trigonal planar and trigonal pyramidal shapes. The prefix tetra means 4, so the presence of 4 terminal atoms produces a tetrahedral shape. The number of lone electron pairs can help you determine the shape of a molecule. Look at the numbers of lone electron pairs associated with the central atom. Notice that, with the exception of a tetrahedral, a lack of lone electron pairs produces shapes in a single plane. These are the linear and planar shapes. As the number of lone pair of electrons around a central atom increases, the bond angle between the terminal angles decreases. The tetrahedral, trigonal pyramidal, and bent shapes all have 4 regions of electrons around the central atom. However, the shapes are different because the number of lone electron pairs around the central atom of each molecule is different. In 1962, a team of scientists created xenon tetrafluoride, the first simple compound composed of a noble gas. Prior to this creation, xenon was believed to be inert, or unable to react with other elements to create compounds. Why do you think the noble gas xenon is able to bond with other elements? The main rule used to determine a correctly drawn Lewis structure is the octet rule. The octet rule states that atoms gain, lose, or share electrons to gain a stable electron configuration with 8 valence electrons. However, some molecules don't obey the octet rule. These molecules have either fewer or more than 80 electrons surrounding the central atom. One exception to the octet rule occurs when the total number of valence electrons in a molecule is an odd number. Nitrogen dioxide is an example. The sum of the valence electrons from the nitrogen atom and the 2 oxygen atoms is 17. Because the number of valence electrons is an odd number, the electrons can't be divided evenly into pairs. The Lewis structure for nitrogen oxide therefore shows that the nitrogen atom has only 7 valence electrons. Another rare exception to the octet rule is a compound that has a stable configuration with fewer than 8 valence electrons around the central atom. This configuration is called a suboctet. Beryllium, boron, and aluminum are the elements that are most likely to form compounds with suboctets. Beryllium chloride, boron trihydride, and aluminum trichloride are all examples of compounds that have a suboctet. A molecule with a suboctet, like boron trihydride, can easily form a bond with another molecule, like ammonia, because its central atom lacks a full octet. Boron trihydride can bond with ammonia when the nitrogen atom in ammonia shares its 2 lone pair electrons with the boron atom. A coordinate covalent bond is formed when one atom shares both of its lone electrons with another atom. A molecule with a suboctet tends to be reactive since it has a central atom that can easily share electrons with the atoms of other molecules. The final exception to the octet rule occurs when a central atom has more than 8 valence electrons surrounding it. This type of electron arrangement is called an expanded octet. For example, the molecule sulfur hexafluoride has 6 bonds sharing 12 electrons between the central and terminal atoms. Only central atoms that belong in period 3 or lower on the periodic table can form expanded octets. These atoms can form more than 4 bonds because they can use electrons in the d orbital for additional bonding. Phosphorus, sulfur, and the halogens in period 3 or lower are the elements that most often have expanded octets. Even though xenon is a noble gas with a stable octet in elemental form, it can bond with other atoms. Because xenon is in period 5, it can form expanded octets when bonding. With an expanded octet, xenon can be the central atom in the molecule with more than 8 valence electrons surrounding it. As a result, compounds such as xenon tetrafluoride can be synthesized. Although exceptions to the octet rule exist, it's important to remember the necessary conditions that validate these exceptions. A central atom can have fewer than 8 valence electrons surrounding it only if the molecule contains either an odd number of valence electrons, such as nitrogen dioxide, or a suboctet. In general, only molecules with beryllium, boron, or aluminum as a central atom can form molecules with suboctets. Additionally, a central atom in a molecule can have more than 8 valence electrons surrounding it if it has an expanded octet. However, the central atom must be in period 3 or lower on the periodic table. The most common elements that form expanded octets are phosphorus, sulfur, or a halogen in period 3 or lower. These exceptions to the octet rule will become easier to identify as you practice drawing Lewis structures.